Today I want to go over how you could implement non-transform temporal similarity search, transform temporal similarity search, and compare these to a traditional flat index. So the first thing we're going to do is we're going to install the KDB.AI client. And then let's increase the size a little bit. Let's download our data. Once we download our data, we could import some packages, ignore warnings. We could instantiate this function that's going to tell us how much memory we're actually using. And I already have my environmental variable set. So I'm just going to instantiate my KDB.AI session. And next, let's load this data frame, which is going to get us 50,000 data points for the example stocks AAA and BBB that have the columns time, the symbol, the quantity, and the most important column is going to be our price column. Next, let's drop the table trade TSS if it exists, and let's actually define our schema. So our schema is going to look a little bit like this. We have some metadata columns, our index, our time, our symbol, our quantity, and then we have our price column where we're specifying that we have a TSS index and our similarity metric is going to be L2. So let's run this really quick. And let's actually create our table. So here this is going to take some time to create, but once we create it, we can insert our data into our table. Nice, our data is inserted. Next, let's define some sliding windows. So our sliding windows are going to have 1,000 dimensions. And then what we're basically doing is for every single point, we're going to create a sliding window of 1,000 dimensions. So let's run this and let's create a query vector. And this query vector is going to have 1,000 dimensions as well. And let's look at the first data point, price point, in this query vector, and it looks a little bit like this. So when we look at our vector df, it has a bunch of these sliding windows. And we could actually plot our query window, and we see it looks a little bit like this. So we have a bunch of points over time. And then we could actually run a similarity search using our query window. So let's do that. And what we get are a lot of other windows. And we used index at 100 as our query window. So it makes sense that the most similar result is going to be index 100. That's the exact window that we used to query. And the distance is extremely low. But the other windows that are right next to it are also extremely similar. This makes sense because this window is going to be almost exactly like this window, and same with 101, for example. But we also have some windows outside of this that are similar, but they're all in this range pretty much. Yeah, this makes perfect sense. We could also do an outlier search. So let's search with the exact same query and use a negative number to indicate that we want the 10 vectors or windows that are least similar to our query vector. And let's see the result, and we get a bunch of these windows that are not similar to our query window at all. And we can see that the distance is extremely large between them and the query vector. We could also do a dynamic search. So the thing with a dynamic search is we could actually define and change the size of the query vector that we're searching. So this is a feature of non-transformed similarity search. So let's say we had a smaller query vector which has 50 data points. We could search with 50 data points. And all of these results that we're getting are 50 data points large in terms of their window. And of course, the one we're searching is the closest, and the ones around it are close, but there's a few other ones that are completely far away that are similar to our query vector. Let's try with 500. We could search 500 points as well. And once again, we get results that make a lot of sense. And this is a major advantage because we could search any window we want. Let's say there is a specific pattern that's 50 price points long. Well, we could search 50 price points. We don't have to search a larger window, which might not represent the specific pattern that we're looking at. If this is a spike in the stock price, we only want to look at that spike. We don't really care about the information around that spike as much. We could also do multiple searches. So here we're searching the regular query vector of 1,000 dimensions, and then 500 dimensions, and then 50 data points. And we could search them at the same time, and we get all of these results simultaneously. And now finally, let's look at our memory usage. So let's see how much memory we actually used. And we did not use that much memory. Nice. And let's look at our search timings. And for single search, it took 341 milliseconds. And for multi-search, it took 476 milliseconds. So it makes more sense to do multiple searches at the same time than to do them all sequentially, for example. Finally, let's drop our table to conserve resources. And let's move on to actually transformed similarity search. So transformed temporal similarity search doesn't let you do outlier search, for example, but it has massive memory savings over non-transformed similarity search. So let's actually try it. We're going to install KDB.AI client again, and we're going to download the same exact data as before. Install our dependencies, run this so we ignore warnings, define this function again, and I can connect to my cloud instance because I have my environmental variable set. And now let's load our synthetic market time series data and define the same exact window function. And let's look at our data. So we have these windows defined, and we are ready to insert that data into our index. So let's make sure this trade table doesn't exist yet. And let's look at the schema we're going to use. So first, let's try inserting this into a flat index. And that way we can compare the performance of a flat index with transformed temporal similarity search. So this is just a simple index with a schema that defines some metadata and this price column that has a flat index and uses Euclidean distance as a similarity metric and has 1,000 dimensions. So let's actually create this table. Now, once this table is created, we can insert this data into our table. And notice that for non-transformed temporal similarity search, we actually didn't have to create these windows first. But here, we do have to create these windows so we can insert into our table. And this is going to take a while. All right, so we've managed to insert all of our price data into our flat index. And this took about a minute. And now let's use our 100th vector as our search vector. And let's plot this once again. It's the same exact query vector. And now let's search. And we get these results, and they're the exact same results as we got previously because we're using a flat index. So we're not compressing this data at all. It's an exact search. So we get these results. We have the exact match of the query we're searching, and we have the vectors around it. Now, transformed temporal similarity search can give us basically very similar accuracy. Yes, we are compressing these vectors, but depending on our data, it might give us pretty much the same search results, but use 99% plus less memory. And that's because we're compressing the size of our windows from 1,000 data points down to only 8 in this example. So let's once again make sure we don't have this trade table, so we're dropping it. And then we're going to define our schema. Our schema is going to have some metadata columns, but it's also going to have this price column. And this price column for transform temporal similarity search is going to have a vector index, which here is a flat index with L2 distance or Euclidean distance as our similarity metric. But we're also going to define our embedding, which is how much we're actually compressing our data. So here we're compressing our data to 8 dimensions. We're defining that we're using transformed similarity search. And then we have this insert error, which is basically saying if we have some data that doesn't really match, then we're just going to not insert anything. So let's run this and let's create this table. And this is going to take a second. Once we create this table, we'll be ready to insert our data once again. So let's insert this data into our transformed temporal similarity search table. So now we've inserted all our data, and it once again took around a minute. And we are ready to start searching. So let's search our query vector once again. And what we see is we get pretty much the same results. So we get our query vector as the first result, and we have this price vector here, which has basically a window of 1,000. And we observe that the return indexes lay on either side of our query vector, which makes sense. So we can evaluate the search and we can figure out whether it's correct, but we could guess that it's mostly correct based on the results we get, which is similar to what we've seen in our other searches. But the advantage is we're using way less memory now. So let's calculate the difference in search timings as well. And for our raw search with the flat index, it takes 377 milliseconds, but with transformed TSS, it takes 141 milliseconds. So we get a 2x improvement while using way less memory. And that's it. That's transformed temporal similarity search, non-transformed temporal similarity search, and just using a flat index. So hopefully this video will help you understand when to use each, what are some of the advantages and disadvantages of each option, and how to implement these. I really hope this video was helpful, and I'll see you. Finally, before you do anything else, drop this table as always to conserve cloud resources, and we're good to go.